All right, let's get started. Welcome back. Welcome to Steel Design. I'm going to try and get in the habit of starting to do something like this at the beginning of each lecture. I got a comment from my 103 course that said they really liked the fact that at the beginning of the YouTube videos they could just hit pause and write down everything that they needed to know. So I thought, you know what, I've been meaning to do something like a little announcement slide for all my other classes. I figured, what the heck, let's go ahead and do it. So welcome back to the spring semester. As you see, Huntington gave us a very warm reception today, right? What's it, like 15 degrees? What is it, something like that? What's it? 18? Okay, well, that's better. That's better. What's it? All right, so welcome to Steel Design. Today's going to be pretty basic, just the overall, hey, here it is, of the course. Just so everybody's aware of the schedule, we are going to have our first homework that's going to be assigned on Friday, so you don't have to worry about anything for the rest of the week. What I'm going to do today is go through the syllabus, go through just the basic course operation stuff. We'll get into some very fundamental stuff today. We're going to talk a little bit about LRFD today, which if you've had me for concrete design, then it should be fairly familiar stuff, the whole 1.2 times the dead plus 1.6 times the live stuff. It's probably been a while, but I know you folks who've had me for concrete design have heard all of that. If you have concrete design in an hour, we will discuss it in very significant detail, so don't worry if it goes a little bit like that. So let's start off, let's go through the syllabus. So let me go ahead and pass that out. So let's see, so 1, 2, 3, 1, 2, 5, 6. There's that. You're fine. All right. So I guess good news and bad news in regards to the textbook for the course. There really isn't a textbook for this class. The actual textbook is the steel manual. I'm sure some of you have some friends or whatnot that may have taken this class before, and you might want to borrow it from them. I'm totally okay with that. Just be aware that, and I'll talk about this here in a second, but just be aware that throughout the semester we're going to tab certain important sections of the manual, and if, let's say it's exam 1, you're going to, if you borrow this from a friend, you're going to have to tab, or you're going to have to sift through, like 20 of these, whereas if you had a fresh manual like this, you may only have to sift through like 5 of them or whatnot. So just be aware of that. I'll go over the broad strokes, though, of the syllabus, just to give you all a heads up. Now, the steel manual can be purchased using this student manual discount program. If you look on MU Online, I've posted a PDF of this. It's a coupon code that reduces the price of this book from about $360 to about $130. So, of course, you're going to want to take advantage of it. I'm not pulling the PDF up on the video because then anybody could use the coupon code. So I'm going to go ahead and pass that out. Just, make sure you're using it and just you know the drill. What's that? You already, well. Okay. All right, well, there, you all can. What's that? Yeah, I sent an email out to everybody. I think that's enough. Now, one thing, if you don't already have the manual, that's okay. That's no big deal. We're not going to need the manual like for the first, I'd say, week or so. But you are going to want to get it as soon as possible because starting right around week 2, we are going to use it. Also, another point, I know this thing can seem kind of bulky and whatnot. You really are going to want to bring it to class. We are going to use it in class. There's going to be a lot of times where we'll have a lot of in-class design examples, and you'll really need it with you in order to make sure that you're looking in the right tables, that you're interpreting the beam charts or the KL over R tables or what have you correctly. So make sure that you bring it with you. I know it's clunky and whatnot, but you'll definitely want to have it. Let's see, what else? Grading basis, I think this is pretty typical for a lot of my classes. Attendance is 5%. The homeworks are pretty, they are kind of big, so the homeworks are going to be 35%, and then 3 exams. I would argue of all the classes that I teach, this one is probably the most, or the least comprehensive in terms of its exams. For instance, on exam 2, we're going to have bolted connections and welded connections, and we will not see it again. It will not be on exam 3. Like, I don't like comprehensive exams, but I know, for instance, like structural analysis, it's really tough to not have, or to eliminate that comprehensive nature on the exams, because things like truss analysis tends to pop up here and there. This class, the topics are very separated from exam to exams. I think you will like that. What else? Oh, I'm going to skip through a lot of the pedigree stuff. I'm sure you all are pretty familiar with this. I do want to take a little bit of time and talk about the schedule. This is something I've been working on for a little while. I've taught the course a number of times, so I've got a pretty good idea on what it is that we're going to cover, so from day to day. So I usually don't do this on Monday, Wednesday, Friday classes because there's so many times that we meet. But since I've taught the course a number of times, I figured, what the heck, let's go ahead and break it down. So I have here literally a day-to-day breakdown of what we're going to cover throughout the semester. I've got when the homeworks are going to be assigned, when they're due. A couple things to point out. We're going to have class canceled on Wednesday, January 25th. I have a research trip where I have to travel to Florida. I know, shucks for me. Yeah. But so I'm not going to be here, so we're going to cancel class on Wednesday, the 25th. But a couple things. For those of you that are also taking concrete design, there is a similar schedule. When you look at the two schedules, you're going to find a couple things. No homeworks or exams are going to be on the same day in both classes. Okay, so I did a little bit of work to make sure that didn't happen. Okay, and if you notice throughout the schedule, there are these makeup days. I put those in there for things like snow days and whatnot. Ever since I've been here, we've had snow days during the spring semester. But if we get lucky and everything works well and we're still on schedule, for instance, this day before Thanksgiving break, or for Thanksgiving break, before spring break, we won't meet. Okay, and then during dead week, if everything works out well and we're on task, we'll meet Monday. Wednesday we won't have class, and then we'll just have exam review on Friday. So it'll be a pretty easy week during dead week, and I figured that'd be pretty fair. Does that sound good? All right, anybody have any questions just about the overall, hey, here it is? All right, a couple things, or one other thing that I decided, or I should mention. So I've got here the lecture notes. Let me go ahead and pass those out. Oh, and go ahead and get this started around sign-in sheet. So if you notice here, that, like I said, the only textbook in the class is the steel manual. You do need to get it. I mean, you really can't negotiate the class without it. One of the things I do want you to pay attention to throughout the semester is this thing on the top right of the slide. If you notice, there's a little green box and a star next to it. Anytime that you see that symbol in the or that legend in the notes, that's a point where you're going to want to place a tab in the manual. So for instance, when we talk about, let's say, shear lag, I'll have here's the table in the manual, and I'll have a little tab note on there. You'll want to place one of those little tabs there. It'll make your life a lot easier. No, we don't tab everything. I've really only selected the stuff I think is the most important. I think there's even more tabs in my manual than you'll ultimately end up needing. So hopefully that'll help out. Let's see. One other point I'll mention, and I'll pull this up here in a second. I think most of you all are fairly aware that I tend to use Blackboard pretty heavily for grade reporting and whatnot. think that's enough. If you look on Blackboard already, I'll just pull up mine. You will see that, now I've already got all the notes posted, all of them. Now, if you look, you're only going to be able to see Lecture Notes 1, the ones I handed out today. But I want you all to be aware that everything's going to be on Blackboard. One short? I'm sorry. But I want you to be aware that everything's going to be on Blackboard. So if you miss something, I'll have it up there. And then I'll also do what I typically do, which is right around exam 1 time, right around exam 2 time, I'll pass my notebook around and let you all sift through and see what you have, what you need, etc. All right. Does anybody have any questions in general about course operation? Maybe it'd help if I turn that on. You know, homeworks, you all have the homework schedule. I believe there's a total of 9 homework assignments throughout the semester. Some are longer than others, but they're not bad if you take your time with them. But if the homework's due Wednesday and you're thinking it's Tuesday at 11 p.m., then it might be a good idea to get started on it. That probably won't go well. So if you take your time with them, they're actually pretty doable. So you all know the drill. They're due at the beginning of lecture, and you know, make sure you're neat handwriting, straight edges, and all that. Now on the exams, you do get to use the manual. Okay, you do get to use the manual. You, by and large, wouldn't be able to negotiate the exam without one. Now I'm perfectly fine with starting the exams a little early if you would like. I don't want steel design exams to be a time crunch, but sometimes just because of having to look back and forth throughout the manual, that they can be. It's just sort of the nature of the beast. But if you'd like, we can meet at 8:30 and start the exams a little early. I just don't want you all to have issue with the exam because of time. But we can discuss that when exam time gets closer and closer. But you can use the steel manual. You can use a formula sheet. You all know the drill. You can put anything on the formula sheet except for worked out examples. And there's that. Any questions? All right. So today, what I want to do today and for the next couple of days is talk about really 2 big items. I want to just talk about the general structural engineering process that we're going to engage in, and then I want to talk about loads. You know, when we went through all the stuff in structural analysis, the loads were really just sort of given to you. You know, here's a beam, it has 2 kips per foot, go. Draw a shear diagram, draw a moment diagram, get deflections. But where'd the loads come from? You know, how do you take a building, you know, like this, a multi-story Weisberg Applied Engineering Complex, and whittle a component down to a simply supported beam that has 1.2 kips per foot? Like, how do you get from point A to point B? I want to talk a little bit about that. I'm going to do something a little different. In here, what I've decided to do is talk about lateral loads, so things like wind load and seismic. And then in concrete design, we'll talk about dead loads, live loads, and snow loads. And I did that because if you've already had concrete design, we kind of already talked about that in there anyways. We did live load reduction and tributary area and things like that. I know my folks who already had concrete design, that stuff's starting to hopefully turn the memory banks. But first I want to talk a little bit about project development and specifically what our job is as structural engineers. I think that when you take a class like structural analysis, you sort of get lost in the minutia and the math, and you start thinking, what are my boundary conditions and what's the 4th order differential equation? You keep getting lost in the math. It's like, wait a minute, what are we even doing here? What's our job? You know, we're structural engineers. What is our role in this world called civil engineering? Well, to start, I would argue that being a structural engineer and defining your roles can be a bit different if you're working on something like a building versus something like a bridge. For instance, if you're working on a building project, you are not really the one who's in charge of the project as a whole. Think about it like this. Who do you think was in charge of making this building look the way it does? Well, ultimately the client, whoever's paying for it, but who laid it out? The architect. The architect. Structural engineers in the world of buildings are really a sub for the architect. The architect takes the demands of the client. In this case, the client would be Marshall. Marshall goes to some architectural firm or some A&E firm or something like that and says, I need a new $50 million engineering complex, and I need this many classrooms and this much square footage, and I need it to fit on this lot on 3rd Avenue, and I want it to have this lab and this many faculty offices and what have you. And then the architect has to take that abstract concept from somebody like Marshall. I mean, Marshall's got a lot of smart people at it, but I guarantee you that the folks that were designing the building, I mean, there were some engineers, you know, and for instance, like our dean and whatnot, who were involved in the layout of the building. But in most cases, your client doesn't really have the first clue about the structural engineering aspects. In other words, they don't care whether the building's structure's made out of steel or concrete or popsicle sticks. They don't care. They just want a structure that meets their demands. Okay? So the architect, what their job is to take this abstract concept of a client like Marshall and turn it into a building. Turn it into a building that meets fire codes, that meets ingress and egress requirements, that has all the appropriate square footage. Then the architect gives that building to somebody like us and says, okay, now make the building stand up. Make it structurally sound. Make it able to withstand its occupancy loads and environmental loads like snow and wind and seismic and things like that. That's what our job is. So a lot of what we're going to spend our time on this semester is ensuring that the elements that we design have enough structural strength and safety. And that's sort of our chief target throughout the semester. In other words, if I'm designing, let's say, a bolted connection, make sure that I'm providing enough bolts to safely resist those loads. If I'm designing a column, make sure the column's big enough to withstand the gravity forces and whatnot. That's going to be our primary responsibility throughout this semester. But I want you to be aware that there's a whole bunch of other stuff going on in the background. For instance, whether or not a structure is safe and sound to resist the loads that are applied to it is a completely separate issue from things like day-to-day performance, serviceability. For instance, there are floor beams above this drop ceiling that are supporting the floor loads on the second floor, right? Now, those floor beams hopefully are safe enough to resist those loads since we're under them, but there are plenty of instances where those beams might have sufficient strength, but they might fail deflection criteria. In other words, they're certainly not going to fail or buckle or anything like that, but they're sagging too much. And a lot of times when we design, we're actually designing not based on strength criteria or something like that, but based on limiting deflections or limiting vibrations. You really wouldn't be in a building that's vibrating or shaking so much. Let's say if we were in an industrial facility and there was a lot of vibrating equipment or something like that. We also have to make sure that the structure is able to be built. And this is a big issue, not just in buildings, but in bridge design as well. There are a lot of instances in the world of bridge design where the actual worst case scenario, the worst state of stresses that a lot of these girders see are not in their intact final state, but during construction. If you've got some massive steel girder that's that has to support this, some concrete deck or something, and many times the worst case scenario for the stresses on that girder is before the deck's even placed. Once the deck's placed, the deck's locked in and the bridge isn't going anywhere. But a lot of times we're actually taking the flanges and making them thicker, taking the girders and making them deeper because of its performance during construction, not in the intact final state. Lastly, we have to design a structure that's economically competitive. We can't look at all these load scenarios and just go, when in doubt, make it stout. You know, I know that's a fairly common adage among civil engineers, but you have to understand we have to meet the demands of clients who are, in a sense, bankrolling a lot of these operations. And how do you think it's going to sound when you have a structure that has these massive elements that's going to cost them an arm and a leg? And they say, why? Well, we didn't know what we were doing, so. You know what I mean? So this name should be somewhat familiar by now. I mentioned this last semester in instructional analysis when we did moment distribution. For you ASC folks in the room, you should remember this from the Virginia's conference. But Hardy Cross was a famous civil engineer, not only in the world of structural engineering, but in other areas like H&H and what have you. And he had a very famous quote about structural engineering. He said that strength is essential, but otherwise it doesn't matter. So we're going to spend a lot of the time this semester looking at safety and things like that, but I just want you to have in the back of your head this notion that there's a lot more going on. Yes, sir?
What's H&H?
Hydraulics and hydrology. That's a good question. Now, how many of you are in hydraulics this semester? All right. So remember when at some point you all do pipe network analysis, remember that whole moment distribution stuff we did at the end of structural analysis. It's going to be somewhat related. Instead of carrying over moments, you're going to be carrying over pipe flows and things like that. All right. Y'all remember that? But we didn't do moment distribution with you all, so we didn't do moment distribution that semester. You missed out on it. All right. Structural analysis, folks, is this familiar? All right. Yeah, we didn't have time. Yeah, we didn't have time. We had a shorter semester then, so I cut it out. Remember, we were on 14 weeks then. Don't get me started. What's that? You can complain about anything. I personally will not stop you. So. All right, I do want to walk you a little bit through the process, what it is that happens from start to finish. Now, I'm doing this for a particular building project. Keep in mind, for bridges, things are a lot different. For instance, let's lay a couple things out for bridges, and then we'll go into this. In building design, your client is somebody like Marshall University or John Hancock Insurance or somebody like that who wants to design a new corporate headquarters or something. In bridges, who's your client? The government. We're talking about the state, the DOH. They're your client, okay? So that's point one that completely changes things. There tends to be a far higher degree of regulations that need to be fulfilled since you're using taxpayer dollars. That's point one. Point two, when you look at a building, there's a whole lot more going on in the cost of a building than the structure. I mean, if I take this building, there was far more than just the steel and steel beams and columns and bolts and welds that went into this. There's paint, there's TVs, there's these flat screen TVs in every room. There's desks, there's carpet, there's paint on the walls, there's plumbing, there's electrical. There's a lot of money that went into things for this structure that didn't even have anything to do with the structural system. Okay, but in bridges, that's not the case. All right, in bridges, that's the whole project is the structure. You know, you have a few beams, you have a concrete deck, and then that's it. So in the world of bridges, the responsibility of a structural engineer is a lot different because unlike with buildings where the structural engineer is a sub of the architect and the architect is working for the client, in the world of bridges, the structural engineer pretty much runs the whole project because they're the ones designing the entire system. Okay, so your responsibilities and your work products are a little different in the world of bridges than they are in buildings. Let me go through just a general sort of, hey, here it is for what you would do for buildings. And Granted, a lot of this stuff is fairly similar for bridges, but I just want you to understand that your responsibilities are a little different because the hierarchy is a little different. So at the very beginning, you start off actually defining the project. I mean, the architect and the land developer and whatnot has probably worked with the client to develop a general idea for what it is they want. They need a building with X square feet, this many rooms, these facilities, et cetera, this much parking, and all of that. And then it's time for you as the structural engineer to come in and start roughing out a general idea of what's going on. You'll start off by just making sure you have a pretty good definition of the project. What's the function of the building? Its general layout. What are you designing it for? We'll talk about things later on like risk categories. What are the environmental loads you need to consider, et cetera, et cetera. And then before you even start getting any work done, it's time to start talking a little bit about the money, talking about schedules, fees, how things are going to be communicated, your scope of work, and all that stuff. And then it's time to get the contracting done and get the work started. Once that's done, it's time to start in a preliminary fashion, I guess I should say, laying out the structure. Make sure you've got the criteria down pat, maybe come up with some rough ideas of how deep the beams need to be, the size of the columns, what type of structural type you're going to use. For instance, you think about this. This is a steel framed system, but right down the road, 3rd Avenue parking garage, that's a precast concrete structure, right? Different structures are more appropriate for different systems. Just depends on what's going on. What type of lateral systems are we going to be using? And we'll talk about that in a little bit, in a little bit of detail later on. Are we going to be using brace frames? Are we going to be using moment frames? At some point, we're going to have to talk about the geotechnical requirements. What's going on with the soil properties? What type of foundations are we going to use? Are we going to be using shallow foundations, deep foundations, any piles, any things like that? Stuff matters. Okay. Once you've got that down, as I'm sure you all are or should be aware by now, design is a highly iterative process. There's going to be some back and forth between you and the architect and the client to ensure that the design makes sense. For instance, you look at this room and how many column lines are on this back wall. What is that? 3 or 4 or something like that. Is the client okay with that? I guess they were. But making sure all that stuff makes sense. Make sure that your structural analysis is finalized. Again, highly iterative. Make sure that you've got all your plans drafted out, your construction specs drafted out. Make sure everything is coming together. Then it's time to start going into construction. Before that, though, you have to make sure all your bid documents are taken care of. You're probably going to have bid meetings with contractors and things like that. And then as the project is going on, usually structural engineers are going to be involved in inspection, things like weld inspection, make sure the structure is appropriately plumbed during construction, and things like that. Yes, sir?
So how does the architect just get chosen, at least like for government projects and stuff like that? They don't have an in-house architect. Does that get bid out, or does that just get chosen?
Are you talking about if an architect designs some like federal building or something like that?
Just in general.
Very similar. There's usually a fair amount of vetting in terms of the budget. Because it's taxpayer dollars, there's usually more strict requirements in terms of documenting where their dollars are being spent and what have you. But in the end, it's still sort of the same idea. I mean, the federal government, let's say if they're building a new federal building or what have you, the government is still going to contract that out to some A&E firm to help scope that out, to lay it out and make sure they're fine with it. I'd argue that if it's a government building, sometimes the layout and the guidelines might already be defined for them, and the architect might be doing a little more just grunt work than they would on another project. This isn't for instance, this isn't a government building project, but this is an example. How many of you have been to Virginia Tech's campus before? Okay. If you've been to Virginia Tech's campus and you go to the main area of campus, what can you tell me about the buildings? Anybody, what do the buildings look like? If you've ever been on campus. What's that? There. Yeah. All the buildings on Virginia Tech's campus are covered with a particular stone. Okay. They have a particular stone facade. In fact, it's set forth in Virginia Tech's requirements that if you're on the main area of campus and you stand there, any building that you see must have a facade made out of, it's called hokey stone. Okay. So the architect can't go in and say, well, we're going to use a brick veneer. Nope. Now, that's already decided for them. You know what I mean? So it's a constraint that they would go under. I don't know much of, I'll be the first person to admit, I don't know much about federal institutional design, but I would imagine that architects have a fair number of guidelines that they have to meet. But in the end, the process would be generally the same. That's a good question. Any others? This is good stuff. This is very conceptual and just informational in nature. But this is something that I think that you all as engineers just need to keep in the back of your head just throughout your careers. I have here two plots that are largely saying the same thing, but they're incredibly important. So for instance, here on the left is the ability to influence the cost of a project versus time. In other words, at the very beginning, when you're just in planning stages and you're deciding whether or not it's going to be a brace frame or a moment frame or how many beam lines you're going to use per bay, that's when you really have significant chance to change the final cost of the project. You really can't, once the project, hits the ground running, it's almost like a snowball rolling down the hill. By the time it gets, down to the bottom and it's this big, you really can't do much to stop it. In other words, when you're installing the structure and you're putting together beams and columns, you really can't change the cost of the project by then because you're already too far into it, okay? But on the flip side, you also have to consider the cost of a change over time. For instance, it doesn't really cost much to change your conceptual plan of the project at the very beginning. If you decide after a little bit of work, a brace frame really doesn't make sense, let's go with a moment frame. Well, that doesn't cost anything to change at the very beginning. When you're fabricating the elements and you go, oh, changed my mind, it's time to go with a brace frame, well, that's going to cost a little bit of money, okay? So just make sure you're keeping that in the back of your head, all right? Any questions? All right. Okay. I'm going to talk about this stuff real quick. Now, let me forewarn the folks in the room who have not had concrete design. If you are in concrete design here in about 10 minutes, don't worry, we're going to go over this in very significant detail. But for those of you who have already had concrete design, this should be somewhat familiar. I just want to briefly touch the design philosophies that we typically use in civil engineering, and particularly focus on LRFD. In concrete design, we used LRFD to size beams and columns. We use the same design philosophy in here, and even the same load combinations and load factors. So for you concrete folks, this should be somewhat familiar. I'll touch on this in more detail in the next, in concrete design. But all in all, the reason for even developing what we call a design philosophy, and let me be clear, a design philosophy is just a fancy way of saying how we incorporate safety factors. And you all, regardless of if you had steel or concrete design, you should be fairly familiar with safety factors at this point, am I correct? Now, why do we even use safety factors? I mean, what's the point? Aren't we engineers smart enough that we can account for every single conceivable possibility within a given project? Aren't we smart enough that we can do that? Of course not, yeah. There are things that we are uncertain about, okay? So we use safety factors to address those uncertainties, We design for what we know, but we also know that there are things like load estimation and material quality and things like that that we're not 100% on, so we say, let's apply a safety factor. Now, there's two ways of doing that. or at least two general ways of doing that. One of them, which is probably what you're more familiar with, is just say, let's just use a factor of safety of 2. You know, just take the capacity and divide it by 2, and that's what's usable. And that's fine. In some areas like geotechnical engineering, there's really no other way of doing it. Because any geotechnical engineer will tell you, you can do a boring right here and then a boring right over there and get 2 completely different set of soil properties, right? So because of that, you have to just, you know, use the average properties that you come up with and then incorporate a factor of safety that you think makes sense. Geotech is one of those areas that's highly variable. We're not talking about geotech, though, in here. We're talking about structural engineering, and a lot of the components that we're talking about are manufactured products, things like bolts. In concrete design, things like rebar and whatnot. Those are manufactured products, as well as with beams and columns and things like that. So we can be a little more scientific and a little more refined. What we end up doing is this. We end up developing a design philosophy that's known as load and resistance factor design. And it's just a fancy way of saying that we apply 2 different types of safety factors. We apply safety factors to the loads and safety factors to the resistances. Okay? So the loads are things like dead load, like snow load, like wind load, earthquakes, things like that. For each one of those types of loads, we apply load factors, each one to try and address their specific uncertainties. Okay? Same thing with resistance. We apply different resistance factors to elements experiencing compression versus elements experiencing tension versus things in bending versus things in shear. Each one of those has a particular resistance factor to it. The long and short of what we're trying to do is we're trying to address uncertainty. Now, I think uncertainty, I think probability. Now, I know you all are you just love probability and statistics, right? Just love that stuff, right? I can see, I mention it, and you're just having a hard time containing your excitement over the whole thing, right? The long and short of it is we idealize structural behavior as if it was a bell curve, a normal distribution. In this world, there's no structure that's perfectly safe. That doesn't exist, okay? But if we can manage that level of risk into a uniform level of safety, then that's what we should be going for. And that's what the idea behind load and resistance factor design is. If you were in concrete design, you remember some of these load combinations, like 1.2 times the dead plus 1.6 times the live. Those are the same load combinations that we're using in here. So that's a pretty nice finding. So it's not new, for instance. It's also one of the good reasons why taking steel design and concrete design at the same time go hand in hand. They go very well together because it's not like there's a separate design philosophy in here versus in concrete design. It's the same load combos and whatnot. So it's not like you're having to remember 2 different ways of doing things. It's pretty nice. Now, like I said, we'll go over this in very significant detail here in about, about 10 minutes or so. Does anybody have any questions? I know if where did you get 1.2 and where did you get 1.6? Or we'll discuss that here in a little bit. But what I'm most interested in right now is that you understand the idea behind trying to address uncertainty and how we use safety factors not only for the loads, but safety factors for the resistances as well. We'll get into the specifics and the nitty-gritty details later on. Everybody good? All right. This is what I'm going to do. I'm going to at least try and give you an overview of what it is we're going to talk about with lateral loads, but we're not going to get into very nitty-gritty details in here. We'll start that on Wednesday. But I want to at least begin some stuff on structural loadings. My concrete folks have already seen some of this last year when we did things like tributary area, live load reduction, and things like that. We're going to spend some time doing that as well. But what I wanted to do is say, okay, let's talk about something new in here. And I've mentioned wind loads and seismic loads before, but I never really got into very significant detail. And I said, you know what, we got time. Let's do it. Let's get into some detail. So I want to talk about the different type of loadings. Now, I know you all don't have this slide packet. I'll bring it on Wednesday. But so I just want you to sort of get the general gist of what's going on. Now, our goal here for this portion is to discuss the loads that go on structures. We're going to focus on wind and seismic in here, but we'll review the dead load, live load, and snow load stuff later. One of the big issues that we have to address is where do we get these loads from? In other words, where do you think I would find the degree of snow load for Huntington, West Virginia? You know what I mean? Where do you find that? You know, you have to have some source, some specification. The specification that we tend to use in the world of civil engineering is called ASCE 7. ASCE 7 is a standard, obviously published by ASCE, and it's the minimum design loads for buildings and other structures. And this document basically lays it all out on the table. What are the snow loads for a given area? What are the wind loads for a given area? What's the live load for a school versus the live load for a theater versus the live load for a hospital and things like that? Yes, sir?
Yeah, what if the climate changes? I know in Saudi Arabia, the northern part of Saudi Arabia for the past 5 or 6 years, seen snow, and that wasn't there the past 20 years.
That's a great question, and I probably need to get in the habit of this to repeat the question so that you can hear it on the recording. So the question is, what happens if the loads change? Like if you're in a given region, let's say Saudi Arabia, where the snow loads are suddenly changing or whatnot. It's a great question. And the answer is these come out periodically. Right now we're using ASCE 7 2010, and they're currently trying to adopt ASCE 7 2016, although I guess it should be 2017 and whatnot. But these things get periodically released every so often. And you'll see things like changes in the snow maps and changes in the wind speed maps and things like that. ASCE 7 just recently redid how they address wind altogether. Like that was a very big overhaul to the spec. The way, to get specific on snow, the way that we address snow loads in structural engineering is, first off, there's a host of weather stations around the country that collect snow data for the entirety of the country. And with every edition of this comes the release of a snow map that reports ground snow loads for given regions. Now, the country, to give you an idea, the country has a snow load map, and then there's one particular state that has its own snow load map. Which state that is? Alaska. Alaska has its own snow load map because it's Alaska, right? So every now and then those snow load maps get updated. So I guarantee you there's going to be minute changes from this spec to the next one. That's a good question, all right? Everybody else good on that? This is good stuff. I want to make sure that everybody's clear on this. Now, like I said, in here we're going to talk about lateral loads, and there's really two types of lateral loads that buildings experience. By lateral loads, I want to be clear, I mean loads that are acting this way, okay? Gravity loads are acting up and down. And in the world of structural engineering, there's really two types of lateral loads that buildings experience, and that's wind loads and earthquakes, okay? Now, wind loads are handled a little differently. Do you like my picture? It is not. I have cats. My Corsi Val ratings just dropped. No, I still like dogs.
How many cats?
We have 3. I couldn't handle any more though. Well, honestly, the cats are older, so they really don't. They're pretty lazy, you know. They're pretty lazy, so it's not that bad. What happens is my wife will be like, she'll be watching TV, and then one of the Sarah McLachlan ASPCA commercials comes on, and she's thinking about getting a cat. I'm like, I don't know about that. We handle more than we have 3. But they're older and they're pretty relaxed. I put this picture up here, though, not only for a little bit of humor, but to make a specific point. Gravity loads and lateral loads are handled a little differently in the world of in the world of structural engineering. For instance, gravity loads are things like occupancy, like live load. Us, we are a gravity load. We act up and down, okay? The entire building has to be designed to withstand gravity loads in some fashion or another. In other words, if I was in this classroom, these floor beams would have to resist these loads up and down, okay? But the entire building is not designed to withstand lateral loads, okay? For instance, if we're talking about a car seat, we don't design the entire car seat to hold you back in the event of a collision, right? The entire car seat doesn't hold you back. There is a particular system that we install in that car seat, and it's going to hold you back during a collision, right? We call that system a seat belt. Make sense? We don't design the whole car seat to hold you back. We only design the seat belt to hold you back. We do the same thing in buildings, okay? So for instance, the two primary lateral systems that we use in steel buildings are either braced frames or moment frames. A braced frame is taking literally diagonal bracing elements, almost as if we're treating this entire bay as a big truss, and this is what holds the building up under some lateral effect like a wind or an earthquake event. We don't place those braces everywhere, just in very specific locations. Where we place them is largely a function of two things. We try and get the most structural efficiency that we can out of those braces, but there's also the architect. Architects like nice open windows, and more often than not, they don't like these big diagonal braces covering their windows. So sometimes we've got to be a little crafty where we put them. Another option is to use moment frames, and a moment frame is basically just using a much more rigid frame line along a given set of the structure. There are positives and negatives to using brace frames versus moment frames. These connections for moment frames can tend to be pretty expensive, but you have nice open window space and whatnot. It's just a function of the economy and the price of steel and fabrication at the time. But these are the two primary ones that we use. Let's see. All right. We're starting to get close to where we should probably call it. What we're going to do next time is start to discuss the primary primary load effects that happen laterally on structures, particularly wind and seismic. Wind can get a little complicated because wind pressures increase the taller the building gets, so you have to address that in some fashion or another. And then earthquakes can get a little complicated because they don't even load the building, they accelerate the building. So you have to break out some force equals mass times acceleration stuff and all of that. So that's all I've got for you today. I'll have this slide packet for you next time, and we'll start digging into wind and seismic loads a little bit. Again, you'll get your first homework assignment on Friday. Until then, if you haven't already done so, I would order this now. It should come in within about a week. And that's all we got. We'll see you next time. Well, we'll see you in a few minutes, yeah.